You're good.
Okay, so admittedly, since we're just beginning, it makes sense that just kind of implicitly we would solve this problem in the sense of a Bubnov-Galerkin approach because it's the simplest approach. But depending on how far we get in the course, especially for spline-based FEA, because of how rich the solution and test spaces can be, we do more Petrov-Galerkin even in structures than is common. Because we'll build, for example, test spaces that have maybe certain structure to them that make the linear systems of equations either better conditioned or easier to solve or any of the above. Okay, so this is a Bubnov-Galerkin. I won't talk any more about that. The Galerkin approximation in general means that you find a subspace, which we've done, and then the superscript h always means discrete or finite. So once we're discrete or finite, now we can massage this new discrete weak form into something that we can implement on a computer, which means that we're going to introduce matrices and vectors. So this is a step that I'd like to go through in detail, because even people who do finite elements quite a bit may not fully appreciate this step. Okay, so what we're going to do is we're going to leverage the fact that these guys are discrete. And so what that means is that I can write my test function, delta UH, or my trial solution, UH, as a linear combination of some coefficients times basis functions. And this linear combination is finite. So there's n of them. And so what we're going to do is we're going to take this linear combination and we're going to plug it in to our discrete weak form, and out will pop our matrix equations. So let's go ahead and do this. I want to point out a few things about why we made such a big deal about these objects being symmetric bilinear forms. We're going to use those properties right now. So our discrete problem is find UH in VH such that our discrete weak form, delta UH minus F is equal to 0 for all of our discrete test functions. Okay, now what that means is we can plug in linear combinations now. We'll replace delta UH with our linear combination. And we'll also replace UH with its corresponding linear combination. Oh, there's a typo right there, huh? Okay, F is left as is because it is just some input data. That has to equal 0 for all delta UH in VH. Okay, so now we can use the properties of a symmetric bilinear form to massage this. What do you see immediately as being an obvious next algebraic step here?
Defining that how C and D are related.
Okay, yeah, that's something that we're going to do through this step. What about these sums? Can't I actually pull them out of the, remember that it's called linear, a symmetric bilinear form, which means I should be able to pull these sums right out of the equation. So if I pull that out, then I've got, let's pull out A, this guy first. And A, that's okay, right? Because if you need to convince yourself of this, go back and study the two properties that are listed for a symmetric bilinear form, and you'll see that any linear combination can be separated in this way. It kind of passes through the symmetric bilinear form. Okay, now notice that here's the part where I don't know if people appreciate exactly what happens here, okay? What do we do with this statement? What do we do with this statement? What is an equivalent statement? Now that we know that delta UH can be written as a linear combination of unknown coefficients and basis functions, how can we restate this without losing anything? This is a big deal. It's going to be for all. What's next? It's not going to be delta UH. It's going to be something that is part of delta UH.
Coefficients in V.
There you go. So you have, somebody needs to mute themselves.
Yeah.
But it was like either 17 or an 18. I think it's an 18.
Oh, wow.
And
Okay. All right. So notice, can you guys convince yourselves of this? That this statement is equivalent to this statement? How do you make that argument?
Somewhere earlier, did we decide to define the space of VH to be real?
So where do these CAs come from?
So we're just representing delta UH in its with its basis, right? And so basically any delta UH you could get is just going to be a different linear combination of the basis functions.
Exactly. So how do you define a delta UH? It's by selecting a bunch of CAs. You see that? These are the coefficients. They're just real numbers, so they're in the reals. So if you want a new, once you're in the finite dimensional setting, you can just go right to the coefficients and say, look, if I want a new delta UH, the basis doesn't change, the coefficients do. So if I need an equation to hold for every test function, that's exactly equivalent to saying, I want the equation to hold for every possible coefficient set that I could pick. Same exact statement. And this actually is quite illuminating in a way, right? Because what do you then know about this equation? If this thing has to be equal to 0, right? This whole equation has to be equal to 0 for every possible CA, then what must be true?
Doesn't that mean NA and the sum are orthogonal?
Yes, your statement is right. In other words, are the CAs going to be equal to 0 always? No, some of them are going to be positive. But this has to be equal to 0 for every CA, including the positive ones. The only way that can happen is if this guy right here is equal to 0 for every A, every index A. Do you see that? So in other words, let me erase this.
Why couldn't it be non-zero at the times when CA is 0?
Because it could be, but remember, it has to hold for every possible CA. Think about the logic there. It has to hold for every CA, including the ones that are positive. Okay, so let me maybe draw a few of these. So we have C1, N1, then we have a sum on B, DB, NB, minus F, plus C2, plus Cn. That whole thing has to be equal to 0 for all CA, A equals 1 to N. This is a huge step, guys. It might seem trivial, but this is a big deal, what's happening here. Oh my goodness, what did I just do? Are you kidding me?
Undo button up at the top.
Yeah, just click on the.
Oh, yeah, great.
Control Z.
Okay. Thanks, guys. Okay, I can't tell if this is so simple that I'm just like, do you guys see what has happened here? So maybe somebody could repeat what has happened here. This linear combination has to be equal to 0 for every possible CA that you could pick. So C1, it could be 0 or any other number. C2 could be 0 or any other number, and so on down to Cn. Which means what? That, well, if this is non-zero, this better be 0, right? So you have equation 1. Here's your first equation that has to be satisfied. This equation has to be equal to 0. But so does this one. Here's equation 2. This one has to be equal to 0, all the way up to the nth equation has to be equal to 0. So do you notice now you have how many equations? N equations. And how many unknowns? N unknowns. Okay, you see what's happened here? We've gone from our abstract weak form to a set of a linear system of n equations in n unknowns. Very important. It took me a while to appreciate this. That what's going on here and why this works and how the linear systems that we solve on a computer come to be.
So in this right here, the unknowns are the DBs, and the C's we're saying we don't need to know what those are because
yes,
what's inside has to be 0.
That's right. Because we know that those C's can be anything. They're arbitrary. Remember, because we have this for all. This term here, that means arbitrary when you say for all delta, for all anything, right? So all the C's are doing are telling us what the equations are that we're satisfying.
I think if anyone needs more convincing that those bilinear products have to be 0, say any one of them is non-zero, then I'll choose C's where only the C that's multiplying that one is not 0. And then you get a result that's not 0.
Mm-hmm. No, I see it now. I only got hung up on the because over on the left there was that typo that I didn't catch. And so when I realized that the two summations were going over a different integrand, not A, but also B, then it made sense.
Gotcha.
Okay, let's talk now about, this is a good point to also bring up one other thing. I don't want to do that. We just did that. So let's get rid of this stuff here. I like things like this because you can just stare at it for a while, or a couple years, or a couple decades. And like, it just keeps sinking in more and more, you know, over time. I like that kind of stuff. Let's talk about, do you remember the definition of linear independence? What was the definition of linear independence from our previous lectures? Right, you had a sum, let's say A equals 1 to N, CA, NA equal, if that equals, so you have a sum, and then we said if and only if what?
All the C's are zeros.
Well, wow, those look almost identical, don't? So what more can we learn here? Okay, what in this case, do you notice how we have a summation that's equal to 0? And we're saying that all the C's, in this case, like these C's are arbitrary. Yeah, so what that says is that these, in order for this to be a solvable system of equations, these are the rows of a matrix. Maybe I could, okay, this will be like the first row, the second row. So what do we know about the rows of this matrix? They better be what? Linearly independent. Right? Because the CAs may be non-zero. So it's kind of like in this definition up here, the CAs are the weak forms and the NAs are the C's, right? But it's expressing the same idea, which is we have a linear combination. We've set it equal to 0. These guys are arbitrary. So in order for this to work, then these n equations in n unknowns better be equal to 0. Right? And that's another way of saying that the rows, you know, all of these equations better be linearly independent. And if they are, right, if they are, and it's a square matrix, then you know you can invert the matrix and solve it. Okay, good. Any questions on that? Okay, very important, important point. Okay, so now let's convert this into our system of equations, and let me make sure we see how that happens. Okay, so let's massage this a little further. So we've got NA, sum on B, dB NB minus F equals 0. A equals 1 to N. Let's pull the sum on B out. So we have B dB NA NB minus F equals 0. A equals 1 to N. Why don't we take this F out, right? Again, using the properties of a symmetric bilinear form.
Dr. Scott,
Yep.
you can't pull the dB.
Oh,
out like
yeah,
that.
yeah. Sorry. Thanks, Kyle. Yep, that's a mistake. Let me do this over again. Let's go ahead and do this first. Okay. So I hope that you can see that this is nothing more than an application of the properties of a symmetric bilinear form, right? We've leveraged the linearity. Now, let's go ahead and subtract this over to the right-hand side. Why do we do that? Because this is what we call known data, right? It's given. F is given data. So let's move the known data over to the right-hand side. Let's pull this sum out. Okay, now the matrices and vectors are starting to show themselves. So what is this? If we're starting to think of a matrix, let's go ahead and start writing down what our matrix will look like. How many rows will it have? We can have n rows, n columns, right? Because there's n unknown, there's n equations. What's going to go, let's say, in this 1, 1 slot? What are we going to put right here? Like in the very top left corner of the matrix, what goes here?
So that's going to be your n1, or n equals a equals 1 and nb equals 1 times that d1.
Okay, let's leave the d
Or
out.
d1, yeah, that's right. That's going to be all the whole row.
Yeah, so then this is going to come over to n1 and little n.
So how do you differentiate whether the n is associated with the a or the n is associated with the b? Are they the same if they both have the same subscript?
In this case, they have different subscripts, but they're running over the same index set. They both go from 1 to n.
Yes, but the n, what it represents, is it the same thing?
Yeah, same number. N is like the total number. It could be like 10.
No, I don't mean
I
that.
think the basis functions.
The basis function. So NA equals 1 basis function. Is that the same basis function as NB equals 1?
Yes.
Because they're in the same space.
Because remember, we're doing a Bubnov-Galerkin, which means that everything comes from the same space, and so it has the same set of basis functions. Yeah, that's a good question, because if it was Petrov-Galerkin, we'd have to put something like a tilde or something over there to say that this isn't the same as this N1. But in a Bubnov-Galerkin approach, we don't have to do that. Everything comes from the same space. Okay, so then this is n sub little n, n1, n sub n, n sub n. And we know that these symmetric bilinear forms, they're functionals, right? So these are mappings from VH cross VH into the real numbers. And so we know that these are numbers in our matrix. Okay, so let's give this matrix a name. This matrix shows up so much it has more than one name. Anybody know what is a name that you would use for this thing here?
Stiffness matrix.
It's not a stiffness. It's close, but a stiffness will come later when we have derivative information. It's the other one. What's the other one? That's
Relax.
Connectivity matrix?
No.
No.
Mass
I'm
matrix.
It is the mass matrix. So if you've ever run a problem, you guys know what the mass matrix is, right? That's exactly what this is. when you take just the inner product of basis functions, not derivatives, but their values, you come up with this structure. It's called a mass matrix, coming from the fact that often there will be an acceleration here. In this case, there's not, because our problem is so simple, but in general, it would look something like that. What's another word, maybe more mathematical, for this matrix? When you take the inner product of basis functions in a space and look at the matrix, what do we call that matrix?
Is this the Gramian? Is that the same
Yeah,
thing?
exactly. Gramian matrix. Don't know if there's two, I think there's one M. It's called the Gramian matrix. It's another term you'll see, and if you read from the context of approximation theory, numerical analysis. Okay, great. So there's our matrix, and then this matrix is going to be multiplied by our D's. So we have D1 through D little n. Okay. And then this guy here is a vector, okay? Because F is known, right? So this is a vector. It just runs over the index A, right? So this guy would be N1F, and then this is NF. What do we sometimes call this vector? Anybody know offhand?
The force vector.
Yep, we call that the force vector. Okay, there's our linear system of equations. So we've gone from a energy, right? At the very beginning, we just had this very abstract statement on minimization of distance in a Hilbert space. And we've introduced the machinery required now to quote unquote discretize the problem or make it finite, and out pop matrices and vectors that you've been using for a long time. So how do we know that this is solvable? Meaning there exists a unique, I'm not going to use all this notation. Why add another layer of complexity? There exists a unique solution, UH. That's the question. How do we know that?
Well, part of it is because they're linear. We know they're linearly independent.
That's exactly right. So there are okay, let's talk about the case if the matrix is square. So in this case, the matrix is square, right? So what does it mean? Like if we say the columns, let's look at the column space here, right? These are vectors, right? You see how these are vectors, whether there's column vectors and there's row vectors in the matrix, right? And they both say something about the space. Let's take a look at these vectors that make up the columns of the matrix. What happens if those are linearly dependent? When can that happen? Like how does that happen? How would that happen? Think about where the columns come from. What would engender linearly dependent columns? I'll give you a hint. It has something to do with the basis of VH. if the basis of VH is what is then linearly dependent columns. What about the basis? Basis of VH is what? Linearly dependent, meaning it wasn't a basis at all. If you construct a VH where you think you have a basis, but you don't, the column space will be rank insufficient and you won't be able to invert your matrix. That sounds pretty heinous, doesn't it? So does that ever happen in finite elements?
Could that possibly happen when you're using floating point numbers or something where they don't have enough precision to
Wow, yeah, great.
preserve it?
That is a great, great question. And you're right. So remember, in finite precision, the basis doesn't necessarily have to be perfectly linearly dependent. It just has to be close to within machine precision of being linearly dependent. So can somebody think of a basis that as n gets big, it becomes more and more linearly dependent from kind of a numerical point of view? What am I drawing?
Those are the monomials.
The monomials. You see what's happening? As n goes up, the difference between subsequent basis functions becomes less discernibly different. And so what happens is that these columns, if you were to build a matrix based on this basis and you had a high n, these columns would become more and more close to being linearly dependent, and it would become harder and harder to solve the problem. Okay, so when you're looking at these, this is a really big deal, especially when we get into splines and linear independence is not trivially satisfied. Your basis that you choose to discretize your space with has to be linearly independent, or every linear system you generate from it will not be solvable. So that's a hard constraint. Okay, so that's one problem. What happens if let's say our basis is linearly independent, say our basis is good, but we have problems now in our row space. Let's say our row space, there's linear dependencies in our row space. How can that happen? Anybody, any of you finite element practitioners or scholars out there? How can you get a problem in your row space? You can guess. No. Just anything come to mind?
Well, so I've not admittedly been paying close attention, but if we don't have boundary conditions, is that what you're getting at? I see that you've written down a mass matrix, which may not make sense in that context, but.
Okay, well, yeah, I mean, that's related to, I was thinking of a more fundamental thing, which just means you have linear dependencies in the equations themselves that you're trying to solve, right? And so one way that this happens is through the imposition of constraints. So if you have any kinds of constraints, like boundary conditions or things that there's linear dependencies amongst the constraints, this happens in Lagrange multiplier problems quite a bit, where you're introducing rows for every constraint, those rows, you can engender linear dependencies in the rows. Okay, so this is, from a finite element point of view, this is an extremely important picture for you to have in mind as you think about your methods, because the column space is kind of saying something intrinsic about the quality of your basis, okay, which is one huge part of finite elements. And the row space is saying something intrinsic about your system of equations. Both work together. They both have to work well. And in finite precision arithmetic, it's not good enough to be linearly independent analytically. You have to be linearly independent from the standpoint of the tolerances of your machine. So the monomials are analytically, theoretically, they're linearly independent functions. But if you were to use them to discretize VH, this matrix would be horrible to deal with. And then same thing is if you have a system of equations where you have maybe a whole bunch of constraints being enforced and becoming rows in your matrix, if you're not careful with how you enforce those constraints, then you can get a row space that's deficient. And so this is a nice picture to keep in your mind as you work with finite elements, is that most people know a little bit about the row space. Most finite element people take the column space absolutely for granted because they've never actually really done anything with basis functions. But with splines, both of them are equally important. Okay, great. Let's stop there. I'll stay on. I will stay on for a few minutes and answer any questions that anybody has about anything with regards to the course. But otherwise, we'll stop there. Thanks, everybody.
Thank you.
Thank you.
Hey, Mike. Can I ask a question, Mike?
Uh-huh.
Can you comment a little more on why Petrov-Galerkin lends itself well to the advection problems?
Because you basically numerically construct your weighting space with respect to like the inner product that's engendered by that advective behavior. So you build the physics actually into the weighting space. And yeah, so that's basically how it